So consider the relation on integers where AB is in the relation only if their difference is congruent to 0 mod n. That is, they have the same remainder when dividing by n. So, for example, if A is Kn plus some remainder, and B is Ln plus some remainder, the same remainder, and their difference is K minus Ln. The R's cancel when we subtract, and that's a multiple of n, so we write that A and B are equivalent, modulo n. We want to show it's an equivalence relation. Well, is A equivalent to itself? Well, A minus A is 0. Right? And that's certainly congruent to 0 mod n, so every integer is congruent to itself mod n. Or the other way to think about it is A gives the same remainder when dividing by n as A does. Okay, suppose that A minus B is 0 mod n. Then A minus B is a multiple of n. That's what it means to be 0 mod n. Or we could say A minus B must be in nz. So if A minus B is in nz, then it looks like Kn. Then B minus A is minus K times n. But minus K n is also in nz. So B minus A is also 0 mod n. Therefore, if AB is in this particular relation, and so is BA, so equivalence mod n is symmetric. So we have reflexive and symmetric. Now we got to prove transitive. That's the tough one here. Suppose that A is equivalent to B and B is equivalent to C. Well, then A minus B is a multiple of n, and B minus C is a different multiple of n. And here's the pretty trick. Then A minus B plus B minus C. The B's cancel. That's A minus C is, should be a minus sign there, right? K minus L. Not quick enough, there goes a point. K minus L. But that's a multiple of n, right? K minus L times n. So A minus C is 0 mod n. So we get it, right? So if A is equivalent to B mod n and B is equivalent to C mod n, then A must be equivalent to C mod n. And so this is an important example of an equivalence relation. Okay, I'm not going to go this deep here. This is essentially a proof that equivalence relations partition a set into disjoint subsets. We should study this proof, but I don't want to go over it in class. Just some important ideas here. This symbol, x with square brackets, means the equivalence class of x under the equivalence relation, the set of all things that are equivalent to x. Yeah, this takes a lot of time to go through. Let's just look at an example. Consider the set of equivalence classes mod 6. 0 is equivalent to all those numbers. Essentially, 0, the equivalence class of 0 is Z6, right? So another way to write this is, no, not is 6Z. Yeah. Is 6Z, right? The equivalence class of 1 is just shifted over by 1. So what's another way to write the equivalence class of 1?
6Z plus 1.
1 plus 6Z is the standard way. This is a coset, right? Equivalence class of 2?
2 plus 6.
It's 2 plus 6Z, right? And the equivalence class of 3 is 3 plus 6Z, and the equivalence class of 4 is 4 plus 6Z, and the equivalence class of 5 is 5 plus 6Z. Now suppose I pick an arbitrary element in the equivalence class of 2 and add it to an arbitrary element of the equivalence class of 5. Well, what do the elements in the equivalence class of 2 look like? They look like 2 plus k times 6, right? And what do the elements in here look like? They look like 5 plus L times 6. So if I add them, what do I get? I get 7 plus k plus L. 6. But how do I want to rewrite 7? 6 plus 1. Right? I'm doing arithmetic here. So this is actually 1 plus k plus L plus 1 times 6. And so where do I end up? In which equivalence class? In 1's equivalence class. This is what we're really doing when we do modular arithmetic. We're saying that the answer is independent of which representative I pick. And that's what allows us to do coset arithmetic here. What we're really doing when we do modular arithmetic is we're working in Z mod 6Z. Because that's what that means, is take all the equivalence class, take all the cosets of that guy and do arithmetic on them. And it works. In this case, because 6Z is a normal subgroup, right? It's an abelian group. So that's a nice example of, it turns out, whenever I do this modular setup, whenever I have a normal subgroup and I take all of its cosets, being in a coset is actually being in an equivalence class, and it's another important example of an equivalence relation. Let's do an easy one. Consider the relation of human populations defined by 2 people are connected if they're born in the same country. Show it's an equivalence relation. Now, what do we have to show?
Reflexive.
Reflexive.
metric, and transitive.
Now, P is born in country as P for any person, right? They're born in the same country as themselves. So we have reflexive. What else do we have to show? Symmetric. If P and Q are born in the same country, then what? So Q and P are born in the same country, right? Then trivially, Q and P are. So we have symmetric. How about transitive? If P, Q are born in X, country X, how do I finish up transitive?
Same if Q and
if, nice.
R.
Q, R are also born in X. Are born in the same country, right? Born in Y.
Then P and R are born in the same.
How do I know that X must be Y?
Q can't be born in 2 places.
Perfect. Implies X equals Y, since Q was born in both. In quotes, right? Therefore, I guess we conclude that P and R are born in X. And we have transitivity. this is a partitioning kind of thing. The equivalence classes would be what? Name one equivalence class for this relation.
Born in America.
Sure. People born in America would be one of the equivalence classes, right? All that. So equivalence relations don't necessarily partition into sets of the same size. Because there's a lot more people born in India than there are in Pakistan, right? Or what's the real tiny one? St. Helena, I think, is a country. It's an island with like 10,000 people on it, or 5,000 people. Yeah. So that's why I bring this up. The equivalence classes don't have to be the same size in general. Or the Vatican's also a country, right?
Yeah.
Yeah. And nobody's born there, right? Not supposed to be. Okay. Show that is similar is an equivalence relation on the set of all triangles in the plane. That's one. That's good. Okay, important use of equivalence relations is equivalence relations of cosets. And let's just look at the theorem, because we've already been over the work. If H is a finite subgroup of G, then the size of the cosets is the same. We can do that. We can show the same size always by finding a bijection. And the bijection is listed there. So we define this map. It takes me from, it takes each element of H and multiplies it by G. And essentially by the cancellation law in the group. That's a bijection. And so that gives me both 1 to 1 and on 2. So that means the sets are the same size. And then let's look at theorem 8. The cosets of the subgroup H are equivalence classes under the following equivalence relation. A and B are related, are equivalent, if and only if they're members of the same coset. And the basic idea here is to show that if A is in GH, then GH and AH are the same group. You should study that proof. But this idea that membership in cosets is an equivalence relation that partitions the group into cosets of equal size, that's the two key ideas here. The cosets are all the same size, essentially by the Sudoku rule, the cancellation law. That gives me the branch. That's the basis for the branch. It says if G is a finite group and H is a subgroup, then the size of H divides the size of G because I have K copies of H, right? That make up G. Okay. And I think we're basically out of time. Do this for homework, and this one is also good homework. Your turn on page 35. This is good practice with Lagrange's theorem. And then Friday we'll just have to fly. But it's all review, right? So we've all seen this all before. Just stop the.
Go.
Okay, go ahead.
All right, we have Rene Descartes. He was born March 31st, 1596 in Le Havre, France. He's the youngest of 3 children. His mother was Jeanine Brocard. He died within a year of his birth. And his father, Jacqueline, was a council member for the provincial parliament. The father sent the children to live with the grandmother. They went to a Jesuit college at age 8. He studied rhetoric, logic, mathematical arts. He earned a bachelor's degree at the University of Poitiers at the age of 22. In 1618, he joined the army for the Dutch Republic. A few years after the army, his whereabouts are kind of unknown. In 1928, he moved to the Dutch Republic to enroll in the University of Frankfurt to study mathematics. Sorry, I forgot to do that. He never married, but he had a daughter named Francine, who was born in the Netherlands in 1635. However, she died at age 5 from scarlet fever. I couldn't find much about where he works, but there was one thing that said he acquired the official chair in philosophy at a university of Utrecht, something like that. He published a few works over the next few years, such as Discourse, Optics, Meteorology, Geometry, Meditations on the First Philosophy, and Principles of Philosophy. And he died in Stockholm, Sweden on February 11th, 1650 from pneumonia.
All right, and René Descartes was one of the most influential philosophers in pretty much all of history. He was kind of the Isaac Newton of philosophy, whereas before, originally philosophy was more about feelings and the way, and especially at the time, was biblical interpretations. And he was one of the first to really check to see what could be proven true or not through things, through senses. In French, cogito ergo sum means I think, therefore I am. And he used the method of methodological skepticism to go one by one and just check everything. How do I know that stapler exists, or that this right here exists? And he realized he couldn't, because he couldn't trust his eyes, because he had no way to know whether his eyes were real or not. But the only thing that he could know was real was that his mind was real, because he was questioning his mind. Because you need a mind to be able to question it. And through that, he figured out that, he also figured that mathematics in general were also kind of transcendent verifiable facts, because things like a square will always have 4 sides, and there's no way that it won't. And that through mathematics, you can prove just about anything, including God, which is one of the things he tried to do. He tried to prove that the soul was in the back of your head and one of your cortexes. I don't know which one it was, but it was kind of close to the cerebellum. It was called the seat of the mind. His influence stretched into a lot of fields. He did mathematics, science, and philosophy. And the grids that we do with the x and y coordinates were designed by René Descartes and are used in pretty much every field, especially in linear algebra, calculus, and whatever's beyond that. And that's really most of his works. Most of his works that you would see today, or many of the things he discovered, are pretty simple at this point, kind of almost obvious because of how much is founded on them.
Alright, one of his most famous works as far as math is concerned were the Cartesian planes, as he previously mentioned, what is known as the Cartesian coordinates. He published this in Geometry, I believe is how it's pronounced. It's where he has different discourses for mathematics. And this, he used equations with variables to put dimensions on a plane. So 2 dimensions, 3 dimensions. We use 3 dimensions here in linear algebra. We started off using, I'm going to show you how to use the 2-dimensional, and then I'll show you, we all know about x, y, z, but I'll explain that later. First, you have the equations we plotted. These are the Cartesian coordinates. You get x, and then you get turn to find the y. So for this one, I used 6 and 0. You would pretty much plug the x in here, work the problem out, and you get the y. From there, you plot the x and the y, their coordinate pair, and you plot them, and then you plug the line. That gives you your what we call the slope. As I said, there are 3 sections in 1637 for the geometry. He was the first one to use the letters from the beginning of the alphabet to represent the known numbers, the known data. and he used the last letters of the alphabet as X, Y, Z to represent the unknown data. This is just a picture of the X, Y, Z axes. He also was the first one to use the standard form of an equation. Standard form of an equation of a line. So that's the ABC and then the XY. And we like to use this to get our slope-intercept form here. But he first started off using that from there. That's pretty much it for it works.
Okay, questions from the audience? Okay, this is good. Stop the camera.
Go.
Alright, so we did Arthur Cayley. He was born August 16, 1821 in London, England, and died 26th of January in 1895 in Cambridge. One of the significant events during his time was over in the Americas, the Civil War was happening. His father was Henry Cayley, his mother was Maria Daughtry, and they were both Russian. His father was a merchant, and his brother is Charles, and he was a linguist. In his early years, when he was at 14, he attended King's College and was advised by the school's master to go to the University of Cambridge because he was a mathematical genius. And then from there, at age 17, he went to Trinity College in Cambridge and contributed 3 papers by the age of 20, and then stayed for 4 more years to get his master's degree. His professional life, he was a lawyer for over 14 years and published between 200 and 300 papers. And then he was a professor, and that's when he published his only book, Treatise on Elliptical Functions.
Arthur Cayley was very passionate about mathematicians, and he worked very hard teaching younger kids on how to just figure out the generals of math. And he worked very hard. He wrote many books trying to figure out, trying to teach kids. He's very smart at what he did. He worked very hard to make sure that he could find new theories. He was very outside of the box kind of person. His memoirs on quantics. He developed analytic geometry. Formalized the matrices. Is A plus 0 equals A. Equals 0 plus A. I don't know, it's
He did like all the associativity rules and distributive properties and all those kind of things for matrices. Okay, so his specific contribution to linear algebra was the Cayley-Hamilton theorem, and Cayley is on the left. The theorem says that every square matrix satisfies its own characteristic equation. So if A is an n by n matrix and I sub n is the square identity matrix, then B of lambda equals the determinant of lambda times the identity matrix minus A. And if you substitute matrix A into the characteristic polynomial for lambda, then that gives you the 0 matrix. So I'm going to show you an example.
Need marker?
Yeah. be a 2x2 matrix C. We'll just let it equal 1, 2, 3. Pretty simple. So the theorem says the characteristic polynomials P of lambda equals the determinant of lambda times the identity matrix, which will be a 2x2 because A is 2x2, minus A